So in this video, I want to look at the error in root x. So this is going to be our x-axis error bar. Now this isn't too bad. It's a bit of a strange one to think about. So I want you to remember how we'd normally combine errors together, and then we can figure out what we do with this one. So very, very quickly, if z equaled a times b in an equation, the error in z will be found as delta z over z equals delta a over a plus delta b over b, where a and b are the values, delta a and delta b are the uncertainties in those values, z is the value you calculated, and delta z is what you want, the uncertainty in that. And you'd rearrange this equation by multiplying it by z. Now that's actually more complicated than what we've got. Okay, so we want to know what the error in the value of root x is. So we apply the same idea. The error in root x over the value of root x is only dependent on x. So it's dependent on the root of x, the error in x, divided by the value in x. So if we simply rearrange that to get the uncertainty in x, which is what I need for my error bars, I multiply by the root x and I get that. Now actually we can simplify that down a little bit if you think about it. Just pure algebra actually does simplify down to that. So the error in the root x, which is what I'm plotting on the x-axis, is just the error in x divided by the root of that value for x. So again, you would need to work that out for every value for x. It is going to be different. But this value here is just the uncertainty in x from your table. So you should have that written in the heading. And remember that this value here, it needs to be in meters before it's square rooted. So really you need this to be in meters as well. I know I very often say it doesn't really matter when you're doing these because they're in ratio, but it doesn't quite work as easily in this case. You've got to be a bit careful. So get everything in meters before you do this and you won't go wrong.